representation of points in matrix form. In this video, we are going to see about representation of points in matrix form. In two-dimensional coordinate system, any point is represented in terms of x and y coordinates. The point x, y can be converted into matrix in the following two ways. Row major matrix, that is matrix with a single row. Column major matrix, that is matrix with a single column. The above two matrices are frequently called position vectors. A series of points, each of which is a position vector related to some coordinate system, is stored in a computer as a matrix or array of number. The position of these points is controlled by manipulating the matrix which defines the points. Lines are drawn between the points to generate lines, curves, or pictures. Representation of any 2D object in matrix form. Suppose it is desired to represent any rectangle in matrix form. Then, first of all user has to be aware of its vertices. Let x1, y1 and x2, y2 be the opposite vertices of a rectangle. Then, the four vertices of the rectangle will be x1, y1, x2, y1, x2, y2, x1, y2. Similarly, if an object is to be converted into matrix form, then the only thing which is to be done is write all its vertices row by row. Transformation of points. In this video, we are going to see about transformation of points. The result of the multiplication of a matrix x, y containing the coordinate of a point P and a general 2 cross 2 transformation matrix. The mathematical notation means that the initial coordinates x and y are transformed to x and y are transformed to x asterisk and y asterisk. Special cases. Case 1. As we have multiplied x with the identity matrix, there is no change in the coordinates of point P. The reason is that in matrix algebra, multiplying by the identity matrix is equivalent to the original matrix. Case 2. X asterisk is equal to Ax produces a scale change in the x coordinates of the position vector. Case 3. This yields scaling of both x and y coordinates of the original position vector. B is equal to C is equal to 0. X into T is equal to xy matrix A0 0D is equal to Ax into dy is equal to x asterisk y asterisk. If A not equal to D, then scaling is not equal. If A is equal to D greater than 1, then pure enlargement or scaling of coordinates of P occurs. If a 0 lesser than A is equal to D lesser than 1, then compression of the coordinates of P. Case 4. B is equal to C is equal to 0, D is equal to 1 and A is equal to minus 1. X into T is equal to xy matrix minus 1 0 0 1 is equal to minus xy is equal to x asterisk y asterisk. The reflection through an axis or plane occurs in the above case through y-axis as shown. If b is equal to c is equal to 0, a is equal to 1 and d is equal to -1, then reflection through x-axis occurs if b is equal to c is equal to 0, a is equal to d lesser than 0. Then reflection through the origin occurs. Transformation. In this video, we are going to see about transformation. The term transform means to change. This change can either be of shape, size, or position of the object. To perform transformation on any object, object matrix X is multiplied by the transformation matrix T. X asterisk is equal to X into T, where X asterisk is matrix of transformed object, X is matrix of original object, T is the transformation matrix. The various transformation possible on an object are as follows: rotation, reflection, scaling, shearing. Each of the above transformation is carried out by using a different transformation matrix. Composite transformation. In this video, we are going to see about composite transformation. If a transformation of the plane T1 is followed by a second plane transformation T2, then the result itself may be represented by a single transformation T, which is the composition of T1 and T2 taken in that order. This is written at T is equal to T1 dot T2. Composite transformation can be achieved by concatenation of transformation matrices to obtain a combined transformation matrix. A combined matrix T into X is equal to X into T1 into T2 into T3 into T4 up to Tn, where Ti is any combination of translation, scaling, shearing, rotation, reflection. The change in the order of transformation would lead to different results, as in general matrix, multiplication is not cumulative, that is A dot B not equal to B dot A, and the order of multiplication. The basic purpose of composing transformation is to gain efficiency by applying a single composed transformation to a point rather than applying a series of transformation one after another. For example, to rotate an object about an arbitrary point xp, yp, we have to carry out 3 steps. Translate point xp, yp to the origin. Rotate it about the origin. Finally, translate the center of rotation back where it belongs. Transformation between coordinate system. In this video, we are going to see about transformation between coordinate system. Suppose that we have 2 coordinate systems in the plane. The first system is located at origin O and has coordinate axis xy. The second coordinate system is located at origin O dash and has coordinate axis x dash y dash. If we think of the second system, x dash y dash, as arising from a transformation applied to the first system, xy, we say that a coordinate transformation has been applied. We can describe this transformation by determining how the x dash, y dash coordinate of a point P are related to x, y coordinates of the same point. This is usually accomplished with the help of translation. Translation and homogeneous coordinates. In this video, we are going to see about translation and homogeneous coordinates. The origin of the coordinate system does not change with respect to transformations. But when the origin is changed, that is, origin is other than 0, 0, it is necessary to be able to modify the position of the origin, that is, to transform every point two-dimensional plane. This can be achieved by translating the origin or any other point in 2D plane. Then is x asterisk is equal to ax plus cy plus m, y asterisk is equal to bx plus dy plus n. It is not possible to introduce the constant of translation m, n into the general 2 cross 2 transformation matrix because there is no place to put the value of m and n. This can be achieved by introducing homogeneous coordinates. The homogeneous coordinates of non-homogeneous vector xy are x dash y dash h, where x is equal to x dash by h and y is equal to y dash by h, and where h is any real number. One set of homogeneous coordinates is always of the form x, y, 1. We select this form to represent the position vector xy in physical xy plane systems. All other homogeneous coordinates are of the form hx, hy, h. There is no unique homogeneous coordinate representation, that is 8, 4, 2, 12, 6, 3, 16, 8, 4, all represent the physical point 4, 2. The general transformation matrix is now 3 cross 3, that is, here A, B, C, D of upper 2 cross 2 submatrix have exactly the same effect as discussed earlier, and extra variable m, n are the transformation factors in x and y directions. Rotation. In this video, we are going to see about rotation. X asterisk y asterisk 1 is equal to x, y, 1 matrix 1, 0, 0, 0, 1, 0, m, n, 1 is equal to x plus m, y plus n, 1. The pure 2D translation matrix is allowed to shift the point at a desired location. This section aims at enabling you to derive the transformation matrix for rotating any object by some angle theta. Consider a position vector from origin to point P of xy. Let r be the length of vector and phi be the angle of vector with x-axis as shown in the below figure. It is required to rotate the point P by an angle theta in anti-clockwise direction. The point P is now shifted to point P asterisk, that is x asterisk, y asterisk. The position vector P is equal to xy is equal to r cos phi r sin phi, and P asterisk is equal to x asterisk y asterisk is equal to r cos theta plus phi r sin theta plus phi. First, let us find the value of x asterisk in terms of x, y and theta. X asterisk is equal to r cos theta plus phi. X asterisk is equal to r cos theta cos phi minus r sin theta sin phi. Since x is equal to r cos phi, y is equal to r sin phi. Therefore, x asterisk is equal to r cos phi into cos theta minus r sin phi into sin theta. X asterisk is equal to x cos theta minus y sin theta. Let us find the value of y asterisk in terms of x, y and theta. Y asterisk is equal to r sin into theta plus phi is equal to r sin theta into cos phi plus r cos theta into sin phi is equal to r cos phi into sin theta plus r sin phi into cos theta. Since x is equal to r cos phi, y is equal to r sin phi. Therefore, y asterisk is equal to x sin theta plus y cos theta. In matrix form, x asterisk is equal to x into t. X asterisk y asterisk is equal to xy into t. Substituting value of x asterisk and y asterisk, we get x cos theta minus y sin theta into x sin theta plus y cos theta is equal to xy into t. Hence, matrix cos theta sin theta minus sin theta cos theta is equal to t. Thus, the transformation matrix for 2D rotation is T is equal to matrix cos theta sin theta minus sin theta cos theta. T is equal to cos square theta plus sin square theta is equal to 1. T is equal to matrix cos theta sin theta minus sin theta cos theta. T to the power of minus 1 is equal to matrix cos minus theta sin minus theta minus sin theta cos minus theta is equal to matrix cos theta minus sin theta cos theta. Now, T into T to the power minus 1 is equal to matrix cos theta sin theta minus sin theta cos theta, matrix cos theta minus sin theta cos theta is equal to matrix cos square theta plus sin square theta minus cos theta sin theta plus sin theta cos theta, cos theta sin theta plus sin theta cos theta, sin square theta plus cos square theta is equal to matrix 1 0 0 1 is equal to 1. Suppose we want to rotate P asterisk back to point P, that is to perform the inverse transformation or rotation. The required angle is minus theta. Therefore, the required transformation matrix is now rotation about an arbitrary point. Rotation occurs only about the origin, but now our aim is to rotate the object about a point other than origin. For this purpose, homogeneous coordinate system will provide a method to accomplish rotation about any point. This can be accomplished in the following order. Step 1. Translate the object or body at the origin, that is translation. Step 2. Rotate by any angle as given, that is translation. Step 3. Translate back to its original location, that is inverse translation. In matrix form, it can be shown as follows. T is equal to TR into R theta into TR the whole power minus 1. TR implies translation matrix. R theta implies rotation matrix by an angle theta. TR to the power minus 1 implies inverse translation matrix. X asterisk is equal to X into T. X asterisk Y asterisk 1 is equal to XY1 matrix 1 0 0 0 1 0 minus M minus N 1 matrix cos theta sin theta 0 minus sin theta cos theta 0 0 0 1 matrix 1 0 0 0 1 0 M N 1. X asterisk Y asterisk 1 is equal to XY1 matrix 1 0 0 0 1 0 minus M minus N 1 matrix cos theta sin theta 0 minus sin theta cos theta 0 M N 1. X asterisk Y asterisk 1 is equal to XY1 matrix cos theta sin theta 0 minus sin theta cos theta 0 minus M cos theta plus N sin theta plus M minus M sin theta minus N cos theta plus N 1. X asterisk Y asterisk 1 is equal to XY1 matrix cos theta sin theta 0 minus sin theta cos theta 0 minus M cos theta minus 1 plus N sin theta minus N cos theta minus 1 minus M sin theta 1. Reflection. In this video, we are going to see about reflection. The term reflection means to simply reflect an object in the plane mirror. The image is made on the opposite side. The reflection is also described as a rotation by 180 degrees. The concept of reflection has been depicted in the figure. Point A, when reflected about y-axis, is displayed as A2, and A, when reflected about x-axis, is displayed as A1. Due to reflection, the image is of the same size but on opposite quadrant, so we need an identity matrix with negative or positive value depending on the situation. Reflection about x-axis, that is y is equal to 0 axis, can be shown as only y value changes by -1 times and x value remains the same. T is equal to matrix 1 0 0 minus 1. Reflection about y-axis, that is x is equal to 0 axis, can be shown as T is equal to matrix -1 0 0 1. Only x value changes by -1 time and y value remains the same. Reflection about the line y is equal to x is T is equal to matrix 0 1 1 0. Reflection about y is equal to minus x is T is equal to 0 minus 1 minus 1 0. Reflection through an arbitrary line. Reflection through the lines x is equal to 0, y is equal to 0, y is equal to x, y is equal to minus x, pass through origin. But when reflection is to be performed about a line other than these, then the process is known as reflection through an arbitrary line. To accomplish this, we use the following procedure that is similarly to the rotation about an arbitrary point. Step 1. Translate the line as well as object so that the line passes through origin. Step 2. Rotate the line and the object about the origin until the line is coincident with one of the coordinate axes. Step 3. Reflect the object through the coordinate axis. Step 4. Apply the inverse rotation about the origin to shift the lines at translated position. Step 5. Apply inverse translation to send back the object, that is, line, to its original position. In matrix notation, T is equal to TR R theta ref R theta to the power minus 1 TR to the power minus 1. TR implies translation matrix. R theta implies matrix for rotation by angle theta. Ref implies reflection about any axis. R theta to the power minus 1 implies inverse rotation. TR to the power minus 1 implies inverse translation. Scaling. In this video, we are going to see about scaling. Scaling means to change the size of object. This change can either be positive or negative. In scaling, parameter Sx and Sy denotes the scale change in the coordinates of x and y respectively. After applying scaling factor or matrix on any object, coordinate is either increased or decreased depending on the value of scaling factors Sx and Sy. If it is greater than 1, the enlargement of the object will occur, and if it is less than 1, compression will occur. Scaling matrix is given as T is equal to matrix Sx 0 0 Sy, where Sx and Sy are scaling factors in x direction and y direction respectively. When two reflection transformation about lines passing through origin are applied successively, result is a pure rotation about origin. Shearing. In this video, we are going to see about shearing. The transformation shearing, when applied to any object, results only in distortion of shape. In shearing, the opposite and parallel layers of any object are simply slided with respect to each other. Shearing can be done either in x direction or y direction. The off-diagonal terms in transformation matrix is responsible for shearing. Hence, the matrix for shearing is Let's consider a unit square and see how shearing affects its shape. Original object after transformation. Representation of points. In this video, we are going to see about representation of points. A point in 3D space is represented by three coordinates x, y, z. By introducing the homogeneous concept, a point in 3D, that is x, y, z, is represented by a four-dimensional position vector, that is x dash y dash z dash h is equal to x, y, z, l into t. Where T is some transformation matrix. Again, the transformation from homogeneous coordinates to ordinary coordinates is given by x asterisk y asterisk z asterisk 1 is equal to x dash by h, y dash by h, z dash by h into 1. Consider this as equation 1. The generalized 4 cross 4 transformation matrix for 3D homogeneous coordinates is the 4 cross 4 transformation matrix in equation can be partitioned into 4 separate sections as the upper left 3 cross 3 submatrix produces a linear transformation in the form of scaling, shearing, reflection and rotation. The 1 cross 3 lower left submatrix produces translation and the upper right 3 cross 1 submatrix produces a perspective transformation. The final lower right hand 1 into 1 submatrix produces overall scaling. This transformation matrix T will be E applied on homogeneous coordinate position vector and will yield shearing, local scaling, rotation, reflection, translation, perspective and overall scaling. Representation of a 3D object in matrix form. 3D transformation can be represented by 4 cross 4 matrices provided we use homogeneous coordinate representations of points in 3D space as well. The generalized 4 cross 4 transformation matrix can be partitioned in 4 separate sections as shown below. The upper left 3 cross 3 submatrix produces a linear transformation. The 1 cross 3 lower left submatrix produces translation. The 3 cross 1 upper right submatrix produces a perspective transformation. The 1 cross 1 lower right submatrix produces overall scaling. Let us consider unit cube with its one corner placed at the origin as shown in the figure, to just let you know how objects are rewritten in matrix form. Now, in order to represent the above object in matrix form, simply write all its points row-wise, one after the other in the following manner. The above matrix in homogeneous form will be translation. In this video, we are going to see about translation. The 2D and 3D transformation can be represented by x dash is equal to t into x, where x dash represents transformed homogeneous coordinates. X represents the untransformed coordinates, and T is the 4 cross 4 transformation matrix, unlike the 3 cross 3 transformation matrix used in 2D. Again, the transformation from homogeneous coordinates to ordinary coordinates is given by if any point P of x, y, z in 3D space is moved to position P dash of x dash y dash z dash such that x dash is equal to x plus del x, y dash is equal to y plus del y, z dash is equal to z plus del z. Del x, del y, del z being the displacement of P in 3 principal directions x, y, z respectively. Then we can express this 3D translation in homogeneous matrix form as Scaling. In this video, we are going to see about scaling. The matrix expression for scaling transformation relative to the coordinate origin will be, but as we already know, this type of scaling reposition an object relative to origin and also changes the shape, that is, relative dimensions of the object. If the scaling parameters, that is Sx, Sy, Sz, are not equal, to induce scaling without allowing any shape change or position change, we have to perform scaling with respect to a point lying on the object itself, and that too using uniform scale factors. Sx is equal to Sy is equal to Sz. Applying methods similar to that used in 2D, the transformation matrix for scaling with respect to a selected fixed point xf, yf, zf can be obtained as rotation. In this video, we are going to see about rotation. Any 2D rotation transformation is uniquely defined by specifying a center of rotation and amount of angular rotation. But these two parameters do not uniquely define a rotation in 3D space, because an object can rotate along different circular paths centering a given rotation center and thus forming different planes of rotation. We need to fix the plane of rotation, and that is done by specifying an axis of rotation instead of a center of rotation. The radius of rotation path is always perpendicular to the axis of rotation. Before considering three-dimensional rotation about an arbitrary axis, we examine rotation about each of the coordinate axes. By convention, positive rotation angles produce counterclockwise rotations about a coordinate axis when looking from positive axis towards the coordinate origin. Rotation about z-axis. If the rotation is carried out about the z-axis, the z-coordinates remains unchanged. That is because rotation occurs in planes perpendicular to the z-axis, while x and y coordinates behave exactly the same way as in 2 dimensions. Rotation of any point P of x, y, z about z-axis by an amount theta is represented by x dash is equal to x cos theta minus y sin theta. Y dash is equal to x sin theta plus y cos theta. Z dash is equal to z. The corresponding transformation matrix in 4x4 form is rotation about x-axis. Here, rotation takes place in planes perpendicular to x-axis, hence x-coordinate doesn't change after rotation, while y and z coordinates are transformed. The expression can be derived similarly as before if we replace the z-axis in figure with x-axis and the other two axes accordingly, maintaining right-handed coordinate system. Looking at the figure, replace z with x, y with z and x with y in equation to obtain the required expressions as y dash is equal to y cos theta minus z sin theta. Z dash is equal to y sin theta plus z cos theta. X dash is equal to x. The transformation matrix is thus Rotation about y-axis. This time we replace z-axis with y-axis and x and y-axis with z and x-axis respectively. Accordingly modifying equation, we get z dash is equal to z cos theta minus x sin theta. X dash is equal to z sin theta plus x cos theta. Y dash is equal to y. The transformation matrix is now multiple transformation. In this video, we are going to see about multiple transformation. Successive transformations can be combined or concatenated into a single 4x4 single transformation that yields the same result. Since matrix multiplication is non-commutative, that is, the order of multiplication is important, A into B is not equal to B into A. The order is determined by the position of the individual transformation matrix relative to the position vector matrix. The matrix nearest to the position vector matrix generates the first individual transformation and the furthest generates the last transformation matrix. It can be expressed as x asterisk is equal to x into t is equal to x into t1 into t2 into t3 up to tn. T is equal to t1 into t2 into t3 up to tn, where here T1 is the first transformation matrix and Tn is the last transformation matrix. Rotation about an axis parallel to coordinate axis. In this video, we are going to see about the rotation about an axis parallel to coordinate axis. The transformation matrices given by the equations 1, 2 and 3 are rotation transformation matrices about x, y and z coordinate axes respectively. Our aim is to rotate the object about axis other than these standard axes. Here, the special case of an axis that is parallel to one of the x, y or z coordinate axis is considered. The below figure is of a body with a local axis system x dash, y dash, z dash parallel to the fixed global axis system x, y, z. Rotation of the body about any of the individual x dash, y dash or z dash local axis is accomplished using the following three steps. Translate the body until the local axis is coincident with the coordinate axis in the same direction. Rotate about the specified axis as given. Translate the body back to its original position. Mathematically, it can be shown as x asterisk is equal to x into t, where t is equal to tr into rx into tr to the power of -1. Here, t implies compound transformation matrix, tr implies translation matrix, rx implies rotation matrix about x-axis, tr to the power -1 implies inverse translation matrix, x implies untransformed or original coordinate matrix, x asterisk implies it represents the transformed coordinate of the body. Rotation about an arbitrary axis in space. In this video, we are going to see about rotation about an arbitrary axis in space. To perform rotation about a line that is not parallel to one of the coordinate axes, we first need to align the line with one of the coordinate axes through some intermediate transformation. Then, the actual specified rotation is performed about that coordinate axis, the expression for which are known standards. Assuming an arbitrary axis in space passing through the point x0, y0, z0 and having direction cosines cx, cy, cz, rotation about this axis by some angle theta is accomplished through the following steps. Step 1. Translate so that the point x0, y0, z0 is at the origin of the coordinate system. The required matrix is TT is equal to matrix 1 0 0 minus x0, 0 1 0 minus y0, 0 0 1 minus z0, 0 0 0 1. Perform appropriate rotations to make the axis of rotation coincident with the z-axis. In fact, we can align the rotation axis with any of the three coordination axes. Here, our choice of z-axis is arbitrary. In general, making an arbitrary axis passing through the origin coincide with one of the coordinate axes requires two successive rotations about the other two coordinate axes. Here, first perform rotation about x-axis until the rotation axis is in the zx plane. Then perform rotation about y-axis until the rotation axis coincides with the z-axis. To obtain the transformation matrix for step 2a and 2b, let us consider a figure where OA vector represents the unit vector along the given axis of rotation and OB vector is a projection of OA vector on the YZ plane. The amount of rotation required in step 2a to bring OA vector in the ZX plane is equal to alpha, the angle between OB vector and Z axis. So for step 2a, that is for rotation about x-axis by angle alpha, the matrix is after step 2a, OA vector becomes OA dash vector and OB vector becomes OB dash vector, both being in the ZX plane. Also the angle between OA dash and Z axis is say beta in the ZX plane, and this is the angle through which the step 2a transformed rotation axis OA dash vector should be rotated about y-axis in clockwise direction in order to coincide with z-axis. Hence, rotation matrix for step 2b is step 3. Rotate about z-axis by the angle theta, the transformation matrix being step 4. Reverse the rotation about y-axis, the matrix being Tr to the power minus 1 gamma beta. Reverse the rotation about x-axis, matrix Tr to the power minus 1 x alpha. Step 5. Reverse the translation carried out in step 1 with the matrix Tt to the power of minus 1. Putting together all these steps, the complete transformation is then reflection. In this video, we are going to see about reflection. Unlike in 2D, reflection of objects in 3D occurs through a plane. In real life, all the mirrors are basically planes in 3D space. Just like 3D rotation, there are some standard reflection and arbitrary reflection guided by the orientation of the reflection plane. Reflection about coordinate planes xy, yz, zx are standard ones and can be easily derived as only dimension or coordinate changes in each case. Reflection about xy plane. After reflection, the object goes on opposite side of the reflection plane along the z direction. So in terms of coordinates, z coordinate gets reversed in sign x dash is equal to x, y dash is equal to y, z dash is equal to minus z. The resulting transformation matrix is thus Tmxy is equal to matrix 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 1. Reflection about yz plane. In this case, after reflection, y and z coordinates remains unchanged, while x coordinate gets reversed in sign x dash is equal to minus x, y dash is equal to y, z dash is equal to z. Tmyz is equal to matrix minus 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Reflection about zx plane. Here, z and x coordinates remains unchanged while y coordinate gets reversed in sign only. X dash is equal to x, y dash is equal to minus y, z dash is equal to z. Tmzx is equal to matrix 1 0 0 0 0 minus 1 0 0 0 0 1 0 0 0 0 1. Reflection about any arbitrary plane. In this video, we are going to see about reflection about any arbitrary plane. If the reflection plane is neither any of the coordinate planes nor parallel to any of them, for our convenience, we may first align the plane with any of the coordinate planes, say xy plane with some additional transformations. Then, we can carry out the necessary reflection in terms of standard reflection about xy plane. This approach is similar to that adopted for 3D rotation about an arbitrary axis. Assuming that the arbitrary reflection plane is defined by a in-plane point P0 of x0, y0, z0 and a vector n is equal to n1i plus n2j plus n3k normal to the plane. Reflection about the plane is accomplished through following steps. Step 1. Translate the system so that P0 of x0, y0, z0 coincides, which is at the origin of the coordinate reference frame. The required transformation matrix is Step 2. Rotate the system such that the normal vector n to the plane at the origin coincides with the z-axis. This will make the reflection plane the z0 coordinate plane. If the matrix representing this step is TR, then TR is equal to TRY, TRX. Here, TRX represents rotation about x-axis and is given by TRY represents rotation about y-axis and is given by. If you recall the same steps performed in case of rotation about an arbitrary axis, then you get Cx, Cy, Cz are the direction cosines of the normal vector n, where Step 3. Reflect the object in question about the xy or z is equal to 0 plane. The corresponding matrix is Tmxy is equal to matrix 1 0 0 0 0 1 0 0 0 0 minus 1 0 0 0 0 1. Step 4. Reverse step 2. First reverse rotation about y-axis, then reverse rotation about x-axis. The matrix is Tr to the power of minus 1 is equal to Trx to the power of minus 1, Try to the power of minus 1. Step 5. Reverse step 1. The inverse translation matrix being Tt to the power of minus 1. Combining the above transformation, the result transformation matrix can be evaluated as T combination is equal to Tt to the power of minus 1, Trx to the power of minus 1, Try to the power of minus 1, Tmxy, Try, Trx, Tt. (3D shearing). In this video, we are going to see about 3D shearing. In 2D transformation, we discussed shear transformations relative to the x or y axis to produce distortions in the shapes of planar objects. In 3D, we can also generate shears relative to the z-axis, and the result is change of volume and 3D shape of any object. This is useful in three-dimensional viewing for obtained general projection transformations. However, it is a bit difficult to visualize the changes object after any shear transformation. For example, a z-axis 3D shear can be expressed as x dash is equal to x plus az, y dash is equal to y plus bz, z dash is equal to z. The following is the corresponding transformation matrix. The effect of this transformation matrix is to alter x and y coordinate values by an amount that is proportional to the z value, while leaving the z coordinate unchanged. 3D shearing transformation can be carried out about the other two principal axes as well. An x-axis 3D shear can be expressed as x dash is equal to x, y dash is equal to y plus ax, z dash is equal to z plus bx. The corresponding transformation matrix is similarly, a y-axis 3D shear can be expressed as x dash is equal to x plus ay, y dash is equal to y, z dash is equal to z plus by. The corresponding transformation matrix is in y-axis, shear boundaries of planes that are perpendicular to the y-axis are shifted by an amount proportional to y. An example of the effect of this shearing matrix on a unit cube is shown in figure, for shearing factors a and b respectively in x and z direction. Projection. In this video, we are going to see about projection. Projection. 3D objects or scenes which are defined and manipulated using actual physical units of measurement in a 3D space has to be transformed at one stage from a 3D representation to a 2D representation. Because finally the image is viewed on a 2D plan of the display device, such 3D to 2D transformation is called projection. To be projected are lines from an arbitrary point called the center of projection through each point in an object. There are different categories of projection depending on the direction of projectors and also the relative position of the center of projection and plane of projection. Terminologies related to projection. There are some basic terminologies related to projection here. Center of projection. It is a point from where projection is taken source or eye position. Projection plane. The plane on which the projection of the object. Projectors. Lines emerging from center of projection and hitting after passing through a point in the object to be projected. Parallel projection. In this projection, the coordinate positions and view plane along parallel lines. Perspective projection. In this projection, object positions are transformed to the view plane along lines that converge to a point called as center of projection. The projected view of an object is determined by calculating the intersection of the projection lines with the view plane. Parallel projection. In this video, we are going to see about parallel projection. When the center of projection is situated at infinite distance such that the projectors are parallel to each other, the type of projection is called parallel projection. In parallel projection, image points are found at the intersection of the view plane with parallel projectors drawn from the object points in a fixed direction. Different parallel projection of the same object result on the same view plane from different projectors. The two basic types of parallel projection are orthographic projection, oblique projection, orthographic projection. Orthographic projection occurs when the direction of projection is perpendicular to the plane of projection, which is shown in the figure. Oblique projection. All other directions of parallel projection causes oblique projection is shown in the figure. Axonometric projections are orthographic projections in which the direction of projection is not parallel to any of the three principal axes. The subcategories of axonometric projections are Isometric projection. The direction of projection makes equal angles with all three principal axes. Dimetric projection. The direction of projection makes equal angles with exactly two of the principal axes. Trimetric projection. The direction of projection makes unequal angles with the three principal axes. An orthographic projection always shows the true size and shape of a single plane face of an object parallel to the projection plane. Transformation matrices and corresponding expressions for orthographic projection onto the coordinate planes are given below. For z is equal to 0 plane, for y is equal to 0 plane, for x is equal to 0 plane. Here, xp, yp, zp is assumed to be the coordinates of the projected points. Using the above mentioned equations, we can get the projected images of the planes, that is object faces, which are parallel to the coordinate planes. So instead of a single orthographic projection, multiply orthographic projections, that is multi-view orthographic projection, are necessary to show the true shape and size of different faces of an object. By combining multiple views like top and bottom view, front and rear view, right side and left side view of the same object, the whole object can be visually reconstructed. The front, right side and top views are obtained by orthographic projection onto the z is equal to 0, x is equal to 0 and y is equal to 0 coordinate planes from centers of projection at infinity on the positive z, positive x and positive y axis respectively. Similarly, the rear, left side and bottom views are obtained by orthographic projection onto the z is equal to 0, x is equal to 0 and y is equal to 0 planes from centers of projections at infinity on the negative z, negative x and negative y axis respectively. For planes like B, C, D in figure, which are not parallel to any of the coordinate planes, we cannot get the true picture by using any of the above transformation equations. To get a true projected picture of the plane BCD, we orient the normal plane so that it becomes parallel to one of the coordinates axes. This makes the plane BCD parallel to one of the coordinate planes, and then it can be orthographically projected to the coordinate plane. Such projected views are known as auxiliary views. Isometric projection. In this video, we are going to see about isometric projection. We have already mentioned that isometric projection is a special case of axonometric projection when the parallel projectors make equal angles with all three principal axes. Isometric projection of an object is obtained by first manipulating, that is rotating, the object about two axes x and y by a fixed amount, followed by orthographic projection onto the projection plane, that is z is equal to 0. Now we have to derive mathematically the degrees of rotation needed about the two axes. Let us consider a unit cube O, A, D, C, E, F, G, B such that the three of its edges OA, OB and OC are along three principal axes x, y and z respectively. Now to obtain isometric projection, the object is to be manipulated such that after orthographic projection, these three edges are equally foreshortened. This implies the foreshortening ratios for each projected principal axis are same in isometric projection. Let us also assume that after the resultant transformation matrix for isometric projection is applied on the unit cube, the points A, that is 1, 0, 0, B, that is 0, 1, 0, C, that is 0, 0, 1, transform respectively to A dash xx, yx, 0, B dash xy, yy, 0 and C dash xz, yz, 0. This happens because the x, y, and z axes on which the points lie transforms respectively to x dash, y dash, and z dash axis. The z coordinates of all the transform points are 0 because finally the points are projected on z is equal to 0 plane. So length of the edge along x-axis after projection is OA dash is equal to square root of xx square plus yx square. Length of the edge along x-axis before projection is OA is equal to 1. So foreshortening factor along x-axis is fx is equal to OA dash by OA is equal to square root of xx square plus yx square. Similarly, foreshortening factors along y and z axis are fy is equal to OB dash by OB is equal to square root of xy square plus yy square, and fz is equal to OC dash by OC is equal to square root of xz square plus yz square respectively. If for isometric projection the cube is first rotated by an angle theta y about y-axis, then through theta x about x-axis, followed by orthographic projection on z is equal to 0 plane, then the transformation expression becomes the concatenated transformation matrix for isometric projection TPR ISO is thus given by TPR ISO is equal to TPR Z is equal to 0 TRX TRY is equal to matrix cos theta y 0 sin theta y 0 sin theta y sin theta x cos theta x minus cos theta y sin theta x 0 0 0 0 0 0 0 0 1. On being operated by the above isometric projection matrix, we get the actual coordinate values of isometric points A dash, B dash, C dash as A dash is equal to xx is equal to cos theta y, comma yx is equal to sin theta y sin theta x, comma 0. B dash is equal to xy is equal to 0, yy is equal to cos theta x, comma 0. C dash is equal to xz is equal to sin theta y, comma yz is equal to minus cos theta y sin theta x, comma 0. Fx square is equal to xx square plus yx square is equal to cos square theta y plus sin square theta y sin square theta x. Fy square is equal to xy square plus yy square is equal to cos square theta x. Fz square is equal to xz square plus yz square is equal to sin square theta y plus cos square theta y sin square theta x. As the foreshortening factors are all equal, fx square is equal to fy square, implying cos square theta y plus sin square theta y sin square theta x is equal to cos square theta x. Replacing cos square theta y with 1 minus sin square theta y and cos square theta x with 1 minus sin square theta x in the above equation, we get sin square theta y is equal to sin square theta x by 1 minus sin square theta x. Similarly, fz square is equal to fy square, which implies sin square theta y plus cos square theta y sin square theta x is equal to cos square theta x, which implies sin square theta y is equal to 1 minus 2 sin square theta x by 1 minus sin square theta x. Equating both the sin square theta y thus obtained, we further get sin square theta x is equal to 1 minus 2 sin square theta x, which implies sin square theta x is equal to 1 by 3, that is, sin theta x is equal to plus or minus square root of 1 by 3, which implies theta x is equal to plus or minus 35.26 degree. Sin square theta y is equal to sin square theta x by 1 minus sin square theta x is equal to 1 by 3 by 1 minus 1 by 3 is equal to 1 by 2, which implies sin theta y is equal to plus or minus square root of 1 by 2, which implies theta y is equal to plus or minus 45 degree. Therefore, there are 4 possible isometric projections. Theta y is equal to minus 45 degree, comma, theta x is equal to plus 35.26 degree. Theta y is equal to minus 45 degree, comma, theta x is equal to minus 35.26 degree. Theta y is equal to plus 45 degree, comma, theta x is equal to plus 35.26 degree. Theta y is equal to plus 45 degree, theta x is equal to minus 35.26 degree. For each case, the foreshortening factor is f is equal to fx is equal to fy is equal to fz is equal to square root of cos square theta x is equal to square root of 2 by 3 is equal to 0.8165. Considering theta y is equal to plus 45 degree, comma, theta x is equal to plus 35.26 degree as a sample case for isometric projection, the transformation matrix becomes the projected isometric view of the cube and principal axis with respect to the original reference frame after TPR ISO is applied on the scene. See how the directions of x and z axis have changed after isometric projection. All the axial lengths have now reduced to 0.8, that is strictly 0.8165 of the original length along the respective transformed axis. OA with 1 unit along x-axis has now become OA dash is equal to square root of 0.7 square plus 0.4 square is equal to 0.8 along x dash. Similarly, OB is equal to 1 transformed to OB dash is equal to 0.8 and OC is equal to 1 transforms to OC dash is equal to square root of 0.7 square plus 0.4 square is equal to 0.8. Oblique projection. In this video, we are going to see about oblique projection. When the angle between the projectors and the plane of projection is not equal to 90 degree, then the projection is called oblique projection. Some common subcategories of oblique projections are Cavalier projection, cabinet projection, Cavalier projection. The direction of projection is so chosen that there is no foreshortening of lines perpendicular to the plane of projection. Cabinet projection. The direction of projection is so chosen that lines perpendicular to the plane of projection are foreshortened by half their lengths. An oblique projection is obtained by projecting points along parallel lines that are not perpendicular to the projection plane. Oblique projection of a point P of x, y, z on the z is equal to 0 plane. POB of xp, yp is oblique projection of the point P, and P or x, y is the orthographic projection of P on the z is equal to 0 plane. Let L be the length of the line joining points POB, xp, yp and P or x, y, theta being the angle made by the line L with x-axis. Then xp and yp can be expressed as xp is equal to x plus L cos theta, yp is equal to y plus L sin theta. Here the length L is a function of z coordinate. If alpha is the direction of projection, that is, the angle made by the projector with the projection plane, then tan alpha is equal to z by L. Thus, L is equal to z by tan alpha is equal to ZL1. When z is equal to 1, L1 is equal to L. xp is equal to x plus z into L1 cos theta. yp is equal to y plus z into L1 sin theta. Considering zp is equal to 0, we get this is the standard matrix expression for oblique projection onto z is equal to 0 plane. When L1 is equal to 0, that is implying alpha is equal to 90 degree, it will represent an orthographic projection on z is equal to 0 plane. For z is equal to 0 plane, commonly used values for angle theta are 30 degree and 45 degree. Two commonly used values of alpha are those for which tan alpha is equal to 1 and tan alpha is equal to 2. For the first case, alpha is equal to 45 degree and the views obtained are called Cavalier Projections. All lines perpendicular to the projection plane are projected with no change in length. For tan alpha is equal to 2, alpha is equal to 63.4 degree and the resulting view is called a cabinet projection. All lines perpendicular to the viewing surface are projected at none half their length. Cabinet projections appear more realistic than Cavalier projections because of the reduction in the length of perpendiculars, that is, depths of objects. Foreshortening factors. The projected length divided by the actual length is called foreshortening factor. The lines or edges which are perpendicular to the plane of projection suffer different shortening in lengths of different values of alpha. The length of perpendicular PR is Z. As the oblique projection of P is POB, the projected length of Z is POB, that is L. Here, the foreshortening factor L by Z is equal to 1 by tan alpha. For alpha is equal to 45 degree, foreshortening factor 1 by tan alpha is equal to 1, and for alpha is equal to 63.4 degree, foreshortening factor 1 by tan alpha is equal to 1 by 2. In case of orthographic projection, alpha is equal to 90 degree, foreshortening factor is 0 as n. This case, the projected length L is equal to 0. In all the above cases, value of theta AY vary. Perspective projection. In this video, we are going to see about perspective projection. To obtain a perspective projection of a 3D object, we transform points along projection lines which are not parallel to each other and converge to meet at a finite point known as the projection reference point or the center of projection. The projected view is obtained by calculating the intersection of the projection lines with the view plane. By varying the position of projection reference point and the projection plane, we will study different standard cases of perspective projection. Case 1. P of x, y, z is any point and Cp of xc, yc, zc is the center of projection. Pp of xp, yp, zp is a perspective projection of P on z is equal to 0 plane with reference to Cp. We have to find the projection matrix. Any point P dash, x dash, y dash, z dash on the line PCP is given by x dash is equal to x plus xc minus x into t. Y dash is equal to y plus yc minus y into t. Z dash is equal to z plus zc minus z into t, where t is the parameter. From the above equation is the parametric equation. For t is equal to 0, x dash is equal to x, y dash is equal to y, z dash is equal to z. For t is equal to 1, x dash is equal to xc dash, y dash is equal to yc dash, z dash is equal to zc. We have to find out for what value of t x dash is equal to xp, y dash is equal to yp and z dash is equal to zp. We assume a case where Cp is on the negative z-axis at a distance d from the origin. Hence, we can write xc is equal to 0, yc is equal to 0, zc is equal to minus d. Putting z dash is equal to zp and zc is equal to minus d in equation 11. Z dash is equal to zp is equal to z plus zc minus z into t, which implies zp is equal to z plus minus d minus z into t is equal to z minus into z plus d into t, which implies t is equal to z minus zp by z plus d. As zp is on xy plane, zp is equal to 0, that is, t is equal to z by z plus d. Putting this value of t in equation 11, we have xp is equal to x dash is equal to x plus xc minus x into t is equal to x plus xc minus x into z by z plus d. But xc is equal to 0 in this case as Cp is on the z-axis. So, xp is equal to x minus xz by z plus d is equal to xd by z plus d is equal to x by 1 plus zd. Similarly, putting the value of t in equation 11 for the value of yp, we have yp is equal to y dash is equal to y plus yc minus y into t is equal to y plus yc minus y into z by z plus d. Here also yc is equal to 0 as Cp is on the z-axis. So yp is equal to y minus yz by z plus d is equal to yd by z plus d is equal to y by 1 plus z by d. So the transformation involved when the point x, y, z is projected on the z is equal to 0 plane with Cp on the z-axis. Here, h is the homogeneous factor and is equal to z plus d. xp, yp and zp can be found by xp is equal to xh by h, yp is equal to yh by h and zp is equal to zh by h. Case 2. To find the transformation matrix for perspective projection of any point P of x, y, z onto the z is equal to k plane from the center of projection Cp at 0, 0 minus d. We know that for z is equal to 0 plane of projection transformation matrix involved is in this problem, the plane of projection involved is z is equal to k plane, which is parallel to z is equal to 0 plane. We adopt a similar technique as we have done when the plane of projection was z is equal to 0 plane. The position of Cp is unchanged. If x dash, y dash, z dash is any point lying on the line PCP, then x dash is equal to x plus 0 minus x into t, y dash is equal to y plus 0 minus y into t, z dash is equal to z plus minus d minus z into t, which implies x dash is equal to x minus xt, y dash is equal to y minus yt, z dash is equal to z minus z plus d into t. Now, when z dash minus zp, then zp is equal to k is equal to z minus z plus d into t, which implies t is equal to z minus k by z plus d. Now, xp is equal to x dash for t is equal to z minus k by z plus d. Therefore, xp is equal to x into 1 minus z minus k by z plus d is equal to x into d plus k by z plus d. Similarly, yp is equal to y dash for t is equal to z minus k by z plus d. Therefore, yp is equal to y into 1 minus z minus k by z plus d is equal to y into d plus k by z plus d. Here, transformation matrix can be found by xp is equal to xh by h is equal to x into d plus k by z plus d. Yp is equal to yh by h is equal to y into d plus k by z plus d. Zp is equal to zh by h is equal to k into z plus d by z plus d is equal to k, where h is equal to z plus d. Basic relationship between Zp and k is established because any point on z is equal to k plane has a projected value of k. Case 3. The plane of projection is defined by a reference point r of x0, y0, z0 lying on that plane and a vector normal to that plane n is equal to n1i plus n2j plus n3k. The center of projection is at origin 0, 0, 0. The point P of x, y, z is to be projected. Any point x dash, y dash, z dash lying on the line PCP is given by x dash is equal to 0 plus x minus 0 into t, y dash is equal to 0 plus y minus 0 into t, z dash is equal to 0 plus z minus 0 into t, or x dash is equal to xt, y dash is equal to yt, z dash is equal to zt. Let x dash is equal to xp is equal to xt, y dash is equal to yp is equal to yt, comma z dash is equal to zp is equal to zt. V is equal to xp minus x naught into I plus yp minus y naught into j plus zp minus z naught into k. The normal vector n is perpendicular to the vector v, hence Vn is equal to 0. That is n1 into xp minus x naught plus n2 into yp minus y naught plus n3 into zp minus z naught is equal to 0. Now replacing the values of xp, xp, xp in the above equation, we get n1 into xt minus x naught plus n2 into yt minus y naught plus n3 into zt minus z naught is equal to 0, which implies t into n1x plus n2y plus n3z is equal to n1x naught plus n2y naught plus n3z naught, which implies t is equal to n1x naught plus n2y naught plus n3z naught by n1x plus n2y plus n3z. This is the value of t for which x dash becomes xp, y dash becomes yp and z dash becomes zp. So, t is equal to d naught by n1x plus n2y plus n3z, where d naught is equal to n1x naught plus n2y naught plus n3z naught. Since xp is equal to x dash is equal to xt, for t is equal to d naught by n1x plus n2y plus n3z. So xp is equal to x d naught by n1x plus n2y plus n3z. Similarly, yp is equal to y d naught by n1x plus n2y plus n3z. Zp is equal to z d naught by n1x plus n2y plus n3z. So the transformation matrix is viewpoints. In this video, we are going to see about viewpoints. Three-dimensional viewing. The 3D viewing process is inherently more complex than the 2D viewing process. In two-dimensional viewing, we have 2D window and 2D viewpoint, and objects in the world coordinates are clipped against the window and are then transformed into the viewport for display. The complexity added in the three-dimensional viewing is because of the added dimension and the fact that even though objects are three-dimensional, the display devices are only 2D. The mismatch between 3D objects and 2D displays is compensated by introducing projections. The projections transform 3D objects into a 2D projection plane. The figure shows the conceptual model of the 3D transformation process. In 3D viewing, we specify a view volume in the world coordinates using modeling transformation. The world coordinate positions of the objects are then converted into viewing coordinates by viewing transformation. The projection transformation is then used to convert 3D description transformation transforms the projection coordinates into the device coordinates. Viewing parameters. As mentioned earlier, we can view the object from the side or the top or even from behind. Therefore, it is necessary to choose a particular view for a picture by first defining a view plane. A view plane is nothing but the film plane in a camera which is positioned and oriented for a particular shot of the scene. world coordinate positions in the scene are transformed to viewing coordinates, then viewing coordinates are projected onto the view plane. A view plane can be defined by establishing the viewing coordinate system or view reference coordinate system as shown in the figure. The first viewing parameter we must consider is the view reference point. This point is the center of our viewing coordinate system. It is often chosen to be close to or on the surface of some object in a scene. Its coordinates are specified as xr, yr, and zr. The next viewing parameter is a view plane normal vector, n. This normal vector is the direction perpendicular to the view plane and it is defined as dxn, dyn, dzn. We know that the view plane is the film in the camera and we focus the camera towards the view reference point. This means that the camera is pointed in the direction of the view plane normal. As shown in the figure, we have world coordinate system which we use to model our object, and we have view plane coordinates which are attached to the view plane. It is possible to obtain the different views by rotating the camera about the view plane normal vector and keeping view reference point and direction of n vector fixed as shown in the figure. At different angles, the view plane will show the same scene but rotated so that a different part of the object is up. The rotation of a camera or view plane is specified by a view up vector v of xup, yup, zup, which is another important viewing parameter. We can also obtain a series of views of a scene by keeping the view reference point fixed and changing the direction of n as shown in the figure. Changing the view plane normal changes the orientation of camera or view plane, giving different views.